Welcome back. In today's explainer, we're diving straight into a crucial topic: how properly setting up motor protection on your Schneider electric Altivar 320 can literally save your equipment from going up in smoke. Whether you're just getting your feet wet with variable frequency drives, or you're a veteran automation engineer fine-tuning a massive panel, getting this right is the absolute baseline of our job. It's the difference between a quick maintenance reset and a completely fried motor.
Here's how we're breaking it down today. We'll start with motor protection theory, then look at the key protection parameters you absolutely need to know. After that, we'll do a quick programming walkthrough, check out a real-world borehole pump case study, and wrap up with the key takeaways.
All right, let's kick things off with Section 1, Motor Protection Theory from First Principles.
So, to really protect a motor, we first got to understand how the drive actually thinks about heat. Heat is, without a doubt, the ultimate enemy of electrical windings. Luckily, modern VFDs have some pretty clever ways of dealing with it. The most important thing to grasp here is the difference between the drive calculating heat and the drive measuring heat. Drive protection uses what we call an I²T model. This is pure math. The drive is essentially looking at how much current the motor is pulling over time and calculating a simulated thermal state. On the flip side, motor protection uses physical PTC or PT100 thermistor probes. These are actually embedded directly inside the motor windings to give us a real-time physical temperature reading.
Now, here's a massive pro tip on how the ATV320 handles this. You don't have to choose. It allows you to combine both methods at the exact same time. And this is a real game changer because using the internal math doesn't disable the external probe monitoring. By running both, you're giving your equipment two independent layers of armor. The math catches overloaded operating conditions, while the physical probe catches environmental issues, like say a blocked cooling vent, that the math might completely miss. For those of you who might be new to VFDs, it helps to think of your motor's thermal capacity kind of like a bucket. Pulling a heavy electrical load fills that bucket with water, which represents heat. Your motor's cooling fan? That's like a drain hole at the bottom. As long as you aren't filling the bucket faster than it can drain, you're golden. But if you overload the motor, the bucket fills up way faster than the fan can cool it. The I²T mathematical model is constantly watching the water level in that bucket. If it gets dangerously close to the top, it steps in, triggers an alarm, and stops the motor before it overflows and burns up.
Moving right along to Section 2, Key Protection Parameters and the real danger of relying on defaults.
Okay, let's uncover a very costly mistake that's hiding in the factory settings. This right here is where perfectly good motors end up getting destroyed just because someone assumed the drive was protecting the motor straight out of the box. Look closely at the ITH parameter. That's your motor thermal current. Check out the factory setting. It defaults to the maximum drive rating. Let me tell you why that's so dangerous. Imagine you buy a 10 amp drive, but you only hook up a 5 amp motor. The drive's math thinks the bucket can hold 10 amps worth of heat. So if your 5 amp motor starts struggling and pulling 8 amps, the motor is literally cooking itself to death. But the drive? It thinks everything is totally fine because it hasn't hit 10 amps yet. You absolutely must change the ITH setting to match your specific motor's nameplate nominal current. No exceptions.
The good news is, once that ITH parameter is dialed in correctly, the drive's math becomes incredibly precise. By default, the ATV320 will trigger a detected error and safely trip the drive when the motor's internal thermal state hits exactly 118% of its rated state. And it's smart too. It'll prevent the motor from restarting until that thermal state cools back down below 100%. Think of it as a built-in mandatory cool-down timer.
Now for Section 3, a step-by-step programming walkthrough.
Let's step right up to the display. If you're standing in front of the drive, you're going to use the jog dial on the front panel to navigate. You'll want to scroll over to the Conf menu, which stands for Configuration, press the dial to enter the full menu, and then scroll your way down into FLT, that's the Fault Management menu, and this entire section is dedicated to setting up your safety boundaries.
Now here is a vital rule of thumb. These fault parameters can only be changed when the drive is completely stopped. Make sure there's no run command active or the drive will just lock you out. Okay, so once you're in that FLT menu, dial in your ITH to match your motor nameplate. Then you want to check THT, which is the motor thermal monitoring mode. Out of the box, it defaults to ACL for standard self-cooled motors. But if you've got a separate forced cooling fan strapped to your motor, you'll definitely want to change this to FCL.
For the engineers out there hooking up physical PTC probes for that second layer of protection, here's some great news. You don't need a separate relay module. You can wire the PTC probe directly into logic input DI6. But there's a little trick to it. You have to physically flip this tiny switch labeled SW2 on the control block over to the PTC position. That converts the digital input into a thermistor reader. After that, you just enable it in the menu we were just looking at. And you know what I genuinely love about this built-in PTC management? It's the smart fail-safe technology. Once you've got it wired and enabled, the ATV320 isn't just passively looking for motor overheating. The drive is actually smart enough to monitor the integrity of the safety circuit itself. It'll trip the drive if it detects a broken wire in the sensor line, or even if it detects a short circuit in the sensor. It is just incredibly robust.
Which brings us to Section 4, our real-world case study on a remote borehole pump.
Let's see how all this theory comes together by imagining an unmanned, remote, submersible borehole pump. This is where proper configuration really proves its worth in gold. Picture a site miles away from any human operator. Over time, sediment starts to build up and causes the pump's intake filter to clog. Naturally, the motor has to work harder and harder to pull water, drawing more and more current. But because a sharp electrician properly set the ITH thermal current parameter during commissioning, the drive's mathematical bucket began tracking that rising heat. Way before the motor windings had a chance to melt, the drive tripped at that 118% thermal state, shut down the power, and fired off a relay to signal a remote alarm back at the main plant.
This real-life scenario perfectly highlights why we absolutely cannot rely on factory defaults. Think about it. If the drive had just been left at its factory default rating, it would have happily pumped maximum current into that struggling motor until the internal windings completely failed. A simple clogged filter would have turned into pulling a massive pump out of the ground, a hugely expensive and time-consuming disaster.
And finally, Section 5, key takeaways to protect your equipment.
To wrap things up, let's distill your biggest takeaways for today. First, understand the difference between the mathematical I²T model and physical PTC probes. Remember that on the ATV320, you can and definitely should use both if your motor has probes. Second, always navigate to the FLT menu when the drive is stopped to set your safety boundaries. And lastly, the most common and destructive mistake in the industry. Never ever leave the ITH parameter at the default drive rating. Always punch in your exact motor nameplate current before you ever hit run.
I want to leave you with a question to chew on today. If your drive is protecting a motor right now, out in the field, do you know for sure if the thermal current is set to the motor's actual rating, or is it just sitting at the drive's default? Check your panels today. Talk to your technicians, because assuming your drive is protecting your motor without actually verifying that HIT parameter, well, that's a massive gamble you really don't want to take with your equipment. Thanks for hanging out with me on this explainer, and I'll catch you on the next one.